Gravitation is a fundamental force of nature that pulls objects toward one another. It's the invisible glue that keeps our feet on the ground, the planets in orbit, and the universe in motion. Every object with mass exerts a gravitational pull on every other object, no matter how far apart they are. This force is what causes apples to fall from trees and gives weight to everything around us. Understanding gravitation helps us explain a wide range of phenomena, from why the Earth orbits the Sun to how galaxies are held together. In this chapter, we'll explore the many ways gravity shapes our world and the universe beyond. Isaac Newton's law of universal gravitation revolutionized our understanding of how objects interact. According to Newton, every mass attracts every other mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This means that the bigger the objects and the closer they are, the stronger the gravitational pull. Newton's insight allowed scientists to predict planetary motion and understand the tides. His law remains a cornerstone of classical physics, providing a mathematical framework for studying gravitational interactions in our everyday lives and across the cosmos. Strength of the gravitational force between two objects isn't constant, it changes with distance. Specifically, as the distance between two objects increases, the gravitational force decreases rapidly. This relationship follows the inverse square law. If the distance doubles, the force becomes 1/4 as strong. This principle explains why astronauts feel weightless in space, far from Earth's surface, and why the sun's gravity keeps planets in orbit even though they're millions of kilometers away. Understanding this relationship helps us predict the motion of celestial bodies and design satellite orbits. The heart of Newton's law is the gravitational constant. Represented by the letter G, this constant is a fixed value that quantifies the strength of gravity in the universe. It allows us to calculate the exact force between two masses, no matter their size or distance. The gravitational constant is incredibly small, which is why gravity is much weaker compared to other fundamental forces like electromagnetism. Despite its smallness, G is essential for understanding everything from falling apples to the motion of galaxies. Scientists have measured G with great precision, making it a key ingredient in physics equations. Gravitational field is a region of space where a mass experiences a force due to gravity. The strength of this field depends on the mass of the object creating it and the distance from its center. For example, Earth's gravitational field is strongest at its surface and weakens as you move away. The concept of a gravitational field helps us visualize how gravity acts at a distance, influencing objects without direct contact. Field lines point toward the mass, showing the direction of the force. This idea is crucial for understanding planetary motion and the behavior of objects in space. Gravity is the invisible hand that guides the motion of planets and satellites. It keeps the moon circling Earth and the Earth revolving around the sun. Without gravity, these celestial bodies would drift off into space. The balance between a planet's forward motion and the pull of gravity creates stable orbits. Satellites launched into space rely on this balance to stay in orbit, allowing them to circle the Earth for years. Understanding how gravity governs orbits is essential for space exploration, satellite technology, and predicting the movement of objects in our solar system. When an object falls freely under the influence of gravity alone, it's said to be in free fall. During free fall, all objects accelerate toward the Earth at the same rate, regardless of their mass. This acceleration is known as g and is approximately 9.8 meters per second squared on Earth. The concept of free fall explains why astronauts experience weightlessness in orbit. They're constantly falling toward Earth, but moving forward fast enough to stay in orbit. Free fall is a key idea in physics, helping us understand motion, energy, and the effects of gravity. Mass and weight are often confused, but they're not the same. Mass is the amount of matter in an object and doesn't change, no matter where you are in the universe. Weight, on the other hand, is the force of gravity acting on that mass. It depends on both the mass of the object and the strength of the gravitational field. For example, your mass stays the same on the moon, but your weight is much less because the moon's gravity is weaker. Understanding this difference is crucial for science, engineering, and everyday life. Gravity doesn't just keep us grounded, it also moves the oceans. The gravitational pull of the moon and the sun causes tides on Earth. As the moon's gravity pulls on the Earth, it creates a bulge in the oceans, leading to high tides. When the sun and moon align, their combined gravity causes especially high and low tides, known as spring tides. This constant movement of water shapes coastlines, affects marine life, and even influences human activities like fishing and shipping. Tides are a powerful reminder of gravity's reach beyond solid ground. Escape velocity is the minimum speed an object needs to break free from a planet's gravitational pull without further propulsion. For Earth, this speed is about 11.2 kilometers per second. If a rocket reaches this velocity, it can leave Earth and travel into space. Escape velocity depends on the mass and radius of the planet. This concept is crucial for space missions, as it determines how much energy is needed to launch spacecraft. Understanding escape velocity helps us explore other planets and the vast universe beyond our home planet. Gravity plays a central role in the birth and evolution of stars and galaxies. In vast clouds of gas and dust, gravity pulls particles together, causing them to clump and eventually ignite nuclear fusion, forming stars. Over millions of years, gravity continues to shape the life cycle of stars, from their formation to their explosive deaths as supernovae. On a larger scale, gravity binds stars into galaxies and galaxies into clusters, creating the grand structure of the universe. Without gravity, the cosmos would be a scattered collection of particles, not the organized universe we see today. Gravitational potential energy is the energy an object has because of its position in a gravitational field. The higher an object is above the ground, the more potential energy it has. When the object falls, this energy is converted into kinetic energy, causing it to speed up. This concept is essential for understanding everything from roller coasters to the motion of planets. Gravitational potential energy helps explain why it takes more effort to lift objects higher and why falling objects accelerate as they drop. It's a key idea in both physics and engineering. Gravity affects the path or trajectory of any object thrown or launched into the air, a projectile. When you throw a ball, gravity pulls it downward, creating a curved path called a parabola. The force of gravity determines how high and how far the projectile will travel. This principle is used in sports, engineering, and even space exploration. By understanding how gravity influences projectiles, we can predict their motion, design better equipment, and solve real-world problems. It's a practical application of gravity that we encounter every day. Pendulum swings back and forth under the influence of gravity. The force of gravity pulls the pendulum downward, while its inertia keeps it moving. This simple motion has fascinated scientists for centuries and is used in clocks, measuring devices, and experiments. The period of a pendulum, the time it takes to complete one swing, depends on its length and the strength of gravity. By studying pendulums, we gain insights into oscillatory motion, energy transfer, and the effects of gravity on moving objects. Orbital motion describes how planets, moons, and satellites move around larger bodies due to gravity. Johannes Kepler formulated 3 laws that explain these motions. His first law states that orbits are ellipses, not perfect circles. The second law explains that planets move faster when closer to the sun. The third law relates the time it takes to orbit to the distance from the sun. Kepler's laws, combined with Newton's work, provide a complete picture of how gravity governs the dance of celestial bodies in our solar system and beyond. Gravity isn't just a local force, it shapes the entire universe. It pulls matter together to form stars, galaxies, and clusters, creating the large-scale structure of the cosmos. Gravity also influences the expansion of the universe, counteracting the force that drives galaxies apart. Without gravity, there would be no planets, stars, or galaxies, just a chaotic sea of particles. By studying gravity, astronomers can trace the history of the universe, understand its current structure, and predict its ultimate fate. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity at the end of their life cycles. The boundary around a black hole is called the event horizon. Inside, the laws of physics as we know them break down. Black holes can grow by pulling in nearby matter and even merging with other black holes. Studying these mysterious objects helps scientists test theories of gravity and understand the most extreme environments in the universe. Albert Einstein's theory of general relativity transformed our understanding of gravity. Instead of viewing gravity as a force, Einstein described it as the curvature of space and time caused by mass and energy. Massive objects like planets and stars bend the fabric of spacetime, and this curvature tells objects how to move. General relativity explains phenomena that Newton's theory couldn't, such as the bending of light by gravity and the precise orbit of Mercury. It's a cornerstone of modern physics and essential for understanding black holes, gravitational waves, and the universe itself. Gravity doesn't just affect objects, it also influences time and space. According to Einstein's theory, strong gravitational fields slow down time, a phenomenon known as time dilation. This effect has been confirmed by experiments with atomic clocks on airplanes and satellites. Gravity also bends the path of light, causing distant stars to appear in different positions. These effects are crucial for technologies like GPS, which must account for time differences caused by gravity. Understanding how gravity shapes time and space reveals the deep connections between matter, energy, and the universe. Gravitational waves are ripples in the fabric of spacetime, caused by massive objects accelerating, like merging black holes or neutron stars. Predicted by Einstein, these waves travel at the speed of light and carry information about their violent origins. In 2015, scientists detected gravitational waves for the first time, opening a new window into the universe. Special detectors, like LIGO, use lasers and mirrors to measure these tiny distortions. Gravitational waves help us study events that are invisible to traditional telescopes, revealing secrets about the most energetic processes in the cosmos. Gravity is at work in our daily lives, from keeping our feet on the ground to making water flow downhill. It's the reason why objects fall when dropped and why we feel a sense of weight. Gravity also affects how we build structures, design vehicles, and even how our bodies function. For example, astronauts in space must exercise regularly to counteract the effects of weightlessness. Understanding gravity helps us solve practical problems and appreciate the forces that shape our world, even when we're not thinking about it. Gravity plays a crucial role in sports, influencing how balls fly, athletes jump, and objects move. Whether it's a basketball arcing toward the hoop or a gymnast flipping through the air, gravity shapes every motion. Coaches and athletes use their understanding of gravity to improve performance, from perfecting a golf swing to mastering a high jump. By analyzing the effects of gravity, sports scientists can design better equipment and training methods. Gravity's influence is everywhere on the field, court, and track, making it a key player in every game. Architects and engineers must consider gravity when designing buildings and bridges. Gravity pulls structures downward, so they must be strong enough to support their own weight and withstand additional loads. By understanding how gravity acts on materials, designers can create safe, stable, and innovative structures. Skyscrapers, suspension bridges, and even simple homes all rely on careful calculations of gravitational forces. This knowledge ensures that buildings remain standing and safe, even during earthquakes or strong winds. Gravity is a silent partner in every construction project. Gravity affects how vehicles move, from cars on the road to airplanes in the sky. Engineers design vehicles to work with or against gravity, depending on their purpose. For example, cars rely on gravity for traction, while airplanes must generate lift to overcome it. Understanding gravity helps improve fuel efficiency, safety, and performance. It also plays a role in designing roller coasters, elevators, and even bicycles. By mastering the principles of gravity, transportation systems become faster, safer, and more efficient. Gravity has a significant impact on our health and well-being. On Earth, gravity helps blood flow, keeps our bones strong, and maintains muscle tone. In space, where gravity is much weaker, astronauts experience muscle loss and bone thinning. Scientists study these effects to develop better exercise routines and medical treatments for both astronauts and people on Earth. Understanding gravity's role in health helps us prepare for long-term space missions and improve life here at home. Modern technology often relies on our understanding of gravity. From launching satellites to designing smartphones with motion sensors, gravity is a key factor. Engineers use gravity to calibrate instruments, develop navigation systems, and even create virtual reality experiences. Technologies like GPS must account for gravitational effects to provide accurate location data. As we continue to innovate, gravity remains a fundamental consideration in the design and operation of new devices and systems. Gravity shapes the natural world, from the flow of rivers to the growth of plants. Water always flows downhill because of gravity, carving valleys and shaping landscapes. Plants sense gravity and grow their roots downward, a process called gravitropism. Animals, too, have adapted to life under gravity, developing strong bones and muscles. By studying gravity's effects on nature, scientists learn how ecosystems function and how life adapts to different environments. Gravity is a silent force that influences every aspect of the natural world. Gravity not only causes tides, but also drives ocean currents. The pull of gravity, combined with the rotation of the Earth, creates complex patterns of movement in the oceans. These currents distribute heat, nutrients, and marine life around the globe. Understanding how gravity influences the oceans helps scientists predict weather patterns, study climate change, and protect marine ecosystems. The interplay between gravity and water is essential for life on Earth and the health of our planet. Space travel would be impossible without a deep understanding of gravity. Engineers calculate trajectories, launch speeds, and orbits based on gravitational forces. Astronauts experience microgravity, which affects their bodies and equipment. Spacecraft use gravity assists, slingshot maneuvers around planets, to gain speed and reach distant destinations. By mastering gravity, we can explore the Moon, Mars, and beyond. Every mission, from launching satellites to landing on other worlds, depends on the principles of gravitation. Gravity remains one of the most fascinating and mysterious forces in the universe. Scientists continue to study its effects, searching for new insights into dark matter, dark energy, and the origins of the cosmos. Advanced experiments, powerful telescopes, and international collaborations are pushing the boundaries of our knowledge. As we learn more about gravity, we unlock new possibilities for technology, space exploration, and understanding the universe itself. The journey to unravel gravity's secrets is far from over, promising exciting discoveries for generations to come.